Okay, so let's start with the last lecture by Laura. And so please, the floor is yours.
Thank you very much. I hope you can hear me okay. All right, good afternoon. Thanks for coming to this last lecture on this topic of celestial holography and celestial amplitudes. So today, the plan is to, now that we have introduced all that we needed to talk about celestial amplitudes, to show you how there are real two-dimensional currents that appear in celestial conformal field theory. And we will discuss also some features of celestial operator product expansions. And then I will try to give you some broad overview of this program of celestial holography, what we have achieved so far, which are the big questions that are still open, and eventually what is the big picture that we want to achieve. So as usual, I will start with a brief recap of the main message of last lecture. So yesterday, we defined what was a celestial amplitudes. And for this, we represented massless particles. The massless particle crossed the celestial sphere. Yes. At a point, then at Z bar and carrying an energy omega, and eventually, and also a helicity if it's spin particle. So these massless scatterers are represented in celestial holography by celestial operators denoted by curly O, which carry a conformal dimension delta and a 2D spin. So the 2D spin is identified simply with the bulk for the helicity of the particle. This operator is inserted at some point Z and Z bar. And delta, importantly, plays the role of the conformal dimension. Which can be written as sum the usual safety language left and right weights, while the spin is the difference of H and H bar. And this mapping, this celestial mapping from a massless scattering to an operator on the sphere was performed via this integral transform, which is a Malin transform. So if you have a scattering of n particles, we will perform a Malin integral over each leg. So for each particle of energy omega I, we will trade it for this complex, a priori complex number, delta. So this is a scattering amplitude written in this convenient boost basis. And in celestial holography, we want to see to which extent we can interpret and what this interpretation will tell us about the holographic structure of quantum gravity and the boundary of flat space. We can interpret this scattering in this boost basis as a correlation function involving these celestial operators on this putative yet to be discovered celestial conformal field theory. So here I recall that the whole point of this was to make this SL2C transformation manifest. Good. So now I will turn to the so-called currents in celestial CFT. So these currents will appear when we take specific integer values of the conformal dimension delta. And we'll call them a conformally soft operator. So indeed, in the second lecture, we saw all these nice equivalences between word identity associated to asymptotic symmetries and soft theorems. So we saw that the soft, I will mostly present current for gravity, but I sketch also the story for the soft photon theorem. So the soft graviton theorem can be interpreted as some insertion of a current. And now the question I want to ask is, you see where we had the soft graviton or soft photon, we're taking the energy omega to 0. But now when in celestial holography, we do no longer have energies to talk about because we have traded energies for conformal dimensions. So what does it mean in the celestial basis to be soft? Well, what people have come to realize is that there is an analogous, or if you want, a dual formulation of softness. But now in the celestial basis, the statement of a particle to be soft. So before we have energetically soft particle, amounted to take on the energy to 0. Now we will be calling in celestial holography a particle which is soft in the conformal sense as a conformally soft particle. And a conformally soft particle or soft operator will be a celestial object for which the conformal dimension take specific integer values. So these objects will play the role of these two-dimensional celestial currents. So which values of delta do we have to look at? Well, today I want to present you two specific values when delta is equal to 1 and delta is equal to 0. Because as you will see, these two quantities will give us the two currents that we have insisted on in the beginning of the lecture, which are the so-called supertranslation current and the famous celestial stress tensor. So let's start with the first object, the supertranslation current. So which value of delta do we have to consider? Well, if you remember yesterday, I presented for you these conformal primary wave functions. And if you remember, there was a primary that was becoming a pure diffeomorphisms for delta equal to 1. And I told you, watch out, when these guys are large gauge transformation, we should not neglect these terms, and subtlety should arise for these values. And indeed, the supertranslation current in celestial CFT is an object, a celestial object, which has conformal dimension equal to 1. So remember, there was the conformal primary wave function that was a pure diffeo for this value. So naturally, since all this business is related to asymptotic symmetries and large gauge transformations, it's natural that something funny happens for this value. And the supertranslation current, more precisely. So if you don't remember what it was, remember that we have these in the usual momentum basis. Let me recall what this was. We had the wired identity associated to supertranslation. For translation symmetry. Where we had statement that this matrix commutes with the charge associated to this symmetry. I think I've written that in this chart when we had different columns, that this wired identity, if you split it into pieces, you put the left on this left-hand side of this equality, is equivalent to inserting this P here, the S matrix, and inserting this object gives you the leading soft Weinberg soft graviton theorem. And if you remember, we had this sort of expression, and I told you this looks like U1 Kac-Moody current, but deformed with this energy omega. And now we will write this not in the, so here I'm still in the old basis, the momentum basis. Now we'll write this in the celestial basis, and we'll see that inserting this object makes some funny, has some funny feature in celestial CFT. So this P inserts a soft graviton. So that was the old basis. Now in the celestial basis, this object will be obtained by taking this so-called conformally soft limit, namely when delta takes some specific values. And actually, it will not be quite exactly the celestial operator when delta goes to 1. So here there is a delta -1 factor. This is just a way to put the pole up rather than down. That comes from omega to 0. Here it will correspond to delta equal to 1. There are different definitions for this, but here I've let the delta equal to 1 in this definition. So you can see that it's not just taking delta equal to 1 of a celestial operator of a spin 2, because I'm talking about gravity operator, but rather I have to take a descendant in the CFT language, so derivative respect to z bar of this operator. And so we can count the weights of this object. So if delta equal 1 and j, the helicity is 2, I can equivalently write in maybe more familiar form in terms of h and h bar. So h is half of the sum of these things. H bar is half of the difference. So the weight of a delta equal 1, j equals 0 celestial operator will be denoted by h comma h bar. So here delta is 1, j is 2. So 1/2 of 1 plus 2, this equals to 3/2. And 1/2 of delta minus j give us -1/2. But you see, this is not P. These are not the weights of P. P is a descendant of this object. So the weights of P are given by the weights of this object. But now, since I'm taking one z bar derivative, this will increase h bar by 1. So it's just the descendancy. So the weight of this supertranslation current is this equal to 3/2, 1/2. So this is something that we are not familiar with in usual CFT. Typically, we talk about Catch-Moody currents, which have 1,0 weight, or stress tensor, which are 2,0. So in particular, this P is not holomorphic, so it's a bit an abuse of language to say it's a current, but yet we will keep calling it like that. And again, now we can rewrite this expression in form of a celestial correlation function. So now in a celestial basis, inserting this supertranslation current, which I recall is in 1-to-1 with expressing Weinberg subgraviton theorem. Now I'm replacing all my in and out state in terms of celestial operators. So let me use this shorthand notation. Okay, here will stand for, we'll carry all the labels of the celestial operators. Celestial operator. So if I insert this current into a celestial, now interpreted as a correlation function on the celestial CFT, I will just obtain that. So I'm just doing an Mellin transform. You can check this very easily. This is just by definition of what is a celestial operator as a Mellin transform of the plane wave. But now you see that before I had this in the momentum basis, I had this omega here in the numerator. Now when I do the Mellin transform, which is here, because I have a delta -1 upstairs, if I want to rewrite this in the operator as a correlation function in a celestial basis, you will see that this is just nothing but the correlation function, but now where the conformal dimension of the operator k is shifted by 1. So the shift by 1 is just because we had an omega here. And when you look at the Mellin transform, if you multiply this by omega, it's the same as shifting delta to 1 in the formula. So again, here we see that the action of the supertranslation current, very importantly, shifts the conformal dimension of the operator in the celestial CFT, which again is something that we don't usually encounter in what people call vanilla 2D CFT. But this is something that we have to deal with in celestial holography. This is just a consequence of supertranslation symmetry. We know that the symmetry is there. So we know that whatever is the dual theory of quantum gravity in flat space written in this basis, it will have to obey this infinite amount of relationship implied by supertranslation symmetry. So this, you see that already just by recasting what we know from the momentum basis to the celestial basis, we already see some features appearing in the dual theory that is starting to tell us in which way this theory is different or familiar to the one we are used to. Is there a question? Are there any questions at this stage on this current? Okay, if not, now let's talk about something a little bit less weird, which is the other current, which is very important, is this stress tensor in celestial CFT. So this is really, as I said before, the discovery that we had super rotation symmetry, and then that this superrotation symmetry were enhancing the global conformal transformation to the full Virasoro group, led people to be very excited and start to dig for more celestial or more CFT2 structure. So how can we get this stress tensor? So celestial stress tensor. So this stress tensor was first obtained in the momentum basis by the work of Andy Strominger and others from really a reverse engineering from the subleading soft graviton theorem. And then they guessed what was the form of an object that they needed to insert in the S matrix so that it's consistent with the symmetry. But in the momentum basis, and in terms of the gravitational solution space, you remember this Bondi expansion I showed you before with the news, the shear. This object is really weird. It's a non-local expression. It's an integral over all null infinity of some derivative of the news tensor. It was a really funny object that they really didn't understand why, how to obtain this in a natural way. And now we can see this object arising more naturally as, again, a conformally soft operator. But there is a subtlety. The subtlety is that this stress tensor involves a so-called shadow transform in CFT. So I'm not sure that this notion is familiar. So let me define what is a shadow transform first. And this shadow transform actually is ubiquitous in the celestial holography program. It shows up. It leads to many confusions. So it's important to discuss it. It's not just a technical point. It's really actually important in understanding what is the spectrum of celestial CFT. Do we have to include all shadow modes or not? There's a lot of debate in the current literature on that. So if you start with the shadow transform of a primary, you have to see primary of weights h and h bar. So again, h and h bar can be traded for delta and j. So what is it? So define like so. Let me write it and then I explain. So the shadow transform will change the conformal dimension, but will return you still a primary. It also flips the 2D spin.
Sorry, Laura, is
yes.
Primary or quasi-primary?
It's a quasi-primary.
Quasi-primary.
Yes. Minus delta. So that's the definition of the shadow. It's an integral over here y and y bar. Okay. So there are some normalization here. It depends on the convention. You can find this definition in paper by Osborne and Dolan, for instance. So you start with the quasi-primary of weight of this dimension, delta and j. You do this integral, which depends on which kind of operator you start from. You will have different powers here in z minus y and z bar minus y bar. And this will return to you another primary, but now with different dimension. Now its dimension will be 2 minus delta. So if I were to write this in terms of h and h bar, you can see that if you start with something, if you start with the primer of these weights, after a shadow, you will have something with 1 minus h and 1 minus h bar. So now it was realized that the stress tensor of celestial CFT arises as the shadow transform of an operator of weights delta equals 0. So I will call stress tensor. Indeed, if I start with something which has weight 0, the shadow transform will give me something which has dimension 2 minus 0, so 2. So this is the stress tensor in celestial CFT. Again, there is this delta here. I write it up front so that the limit when delta goes to 0 of delta times this expression and this you can recognize as the, if you take delta equals 0 in this formula, you will see that this power this exponent become 4 and this is equal to 0. If I start with a spin equal to -2, it will flip the spin. So it will return me something that has h equal 2 and h bar equals 0, which is the dimension we expect from a stress tensor. So it's the shadow of delta equal 0 primary. So again, the realization that this was a stress tensor is really is long. It came pieces by pieces by first this realizing this subleading soft graviton theorems, reverse engineer, and then people say, okay, but there is a basis. Actually, this is what motivated to look at this celestial basis, was to look for a basis where the action of this T was diagonalized. So it's a bit was built on from all that. And here I'm just giving it to you, so you might think, well, where does it come from? How could I have guessed it? Well, just looking at the dimension, you can guess, but this shadow transform is kind of tricky, and it took some time to understand why it has to be like so. But so the main property I want to emphasize on is that indeed, remarkably, we have an object that obeys the wide identity of a stress tensor in a conventional CFT2. Writing down here for you. You can find in any CFT book. Okay, so this is the word identity of a 2D stress tensor, as it should be. Okay. So this equation was checked explicitly from amplitude people. So in particular, Thomas Taylor and Stefan Stieberger, they computed a lot of celestial amplitude, starting from the well-known formula that they have basically invented themselves. So they have checked this formula, checked explicitly. So by brute force, so you start with the momentum basis amplitude, and then you do a bunch of Mellin transform. So they looked at first Einstein-Young-Mills amplitude. So with n gauge bosons and 1 graviton. So it was Fotopoulos and Taylor for this, but then people have been looking at any extension of these sort of facts. So this was really checked by starting with the momentum space Einstein-Young-Mills. You do the Mellin transform, you do a shadow transform, and then you take the limit delta goes to 0, and you land explicitly on this sort of right-hand side. So what it shows is that if you represent gauge bosons by celestial operators, it proved that these celestial CFT operators are indeed full Virasoro primary fields, because this is nothing but the definition of how a Virasoro primary should, if you want, transform. So this is really in one-to-one. So this sort of check proved that CFT operators. So before you see, I was talking about mostly the global part. I was telling you about the SL2C transformation, Möbius transformation. But now you see that when we are coupled to gravity, the presence of superrotations encoded by this stress tensor is enhancing the group so that the operators are now primaries under the full local group, namely they are Virasoro primaries. And this we are very happy because this is something we know very well how to deal with in usual CFT2. So we might hope that because of that, we can exploit the techniques of 2D CFT into this celestial holography program to sort of bootstrap out of the blue the celestial theory. Is there any question on that? Yes.
On the bulk, the computation are done at 3 level, or they are also low computation?
Right. So this work I was mentioning was done at 3 level. The extension to loop corrections is much less understood. There have been some papers on that, but most of the things I'm going to mention are on 3 level.
But yeah, we expect that at loop level, there is it respects exactly the same Virasoro.
So okay, so what happens is that the subleading soft graviton theorem has correction at loop level, but these corrections are 1 loop exact. So it's corrected at 3 level, it's exact in all order of perturbation theory. 1 loop gets correction, but then there is no more correction. And these corrections are, if you want to recast this soft theorem as wide identity of an object, you have to include another contribution to this T here. I'm not entering into this detail, but there is a shifted stress tensor, which is very subtle. It has to do with some vacuum structure of gravity. That's a very good question, but it's under investigation right now. But yes, there is a correction to this T, but it's still a 2,0 thing. But there are some fine details.
Okay, thank you.
Account.
Right. I didn't quite understand why we care that this T was shadow transform of a delta equals 0 operator. Why do we use it?
We care because that's the only way you can get it somehow. If you let's see, how can I explain? So yeah, actually there is an extent to which all objects that are all the currents are actually, if you want to map them to the gravitational phase space, they're actually naturally related not to the celestial operator, but to the shadow operators, all of them. Turns out that I didn't have to talk about that here because the shadow of a delta equal 1 mode has also delta equal 1. But actually, and there is some degeneracy because of that. But actually, there is a pretty funny aspect that if you want to translate with the gravity phase space, naturally what happens, they are somehow all shadow objects. But this is why we care. The reason why we care is because this is somehow what it is. And if you don't have this idea of allowing for a shadow transformation, you would not see this object in the first place. And it's pretty non-trivial, no? That there is something of stress tensor in the boundary of flat space. I mean, why would it be so?
I have not understood this. This is a specific operator, the one from which you construct T, or is a generic operator with delta equal to 0 and j equal to -2?
This one.
Yes.
This O. So yes, this is a generic in the sense that it represents the insertion of a massless graviton on the sphere with spin equal to here to 2 or -2. I have analogous T bar, of course, if I take j equal +2.
Okay,
but
yeah. So suppose you have more than one operator with delta equal to 0 and j equals to -2. How do you know how to generate T, the stress energy tensor?
You mean if I have
Degeneracy, let's say, no?
Yeah, so yeah, so basically what differentiate these operators will be what differentiate their null momenta, for instance. And their null momenta carries a given energy and a point on the sphere. This is the only thing I know when I'm looking at the celestial sphere. And so what I'm saying is that the stress tensor is related to the operator which insert a conformally soft operator because delta takes some specific values. But secretly, actually, you can see that it's equivalent to inserting a soft graviton. So basically, taking omega to 0 is something I'm just stating to you, but taking omega to 0, you can see that from the structure of the amplitude, we'll select some poles when delta takes some integer values. So apart from that, does it answer your question?
Sorry, would I say that the uniqueness of gravity, the fact that there is only one spin 2 massless particle, so if you wish assuming that in the S matrix, which is a very reasonable, then in the celestial CFT has to have a unique, there can be any degeneracy of this operator. So it has to be unique. Otherwise you will have two kind of gravitons and you can't have.
Yeah.
I don't know.
Yes, it's a very strong constraint because so this you can every time I'm writing this relationship, you have to see this as actually an infinite amount of constraint for the CFT to obey. And this is the whole philosophy of this program, is to try to have a bottom-up approach where you derive from what you know constraints on coming from symmetries, and you hope that at some point this constraint will be so strong, there will be so many of them, that it will, if you want, you will isolate a theory that you can identify, or at least you can identify what properties it has for back. Vice and versa. So I will come to that when I talk about where the program stands it. But that's the question was. You can repeat it.
The question was, you should both infer property of the CFT by what you know that gravity should be like. There is just one graviton, so that there must be just one operator with this property. Then understanding property of gravities from, let's say, constraints that I know that there are on CFT, no?
Yeah, so the hope and the thing that people are actively trying to do is that now go in the vice and versa direction that you were mentioning. Namely, can we cook up some theory, a celestial theory, from which we can infer new things that we didn't already know from momentum basis and all this very rich literature on amplitude. And this is an extremely complicated thing to do because basically it would amount to basically have a holographic dictionary fully fledged. So this is an outstanding question to have an intrinsic definition of celestial CFT. Okay, very good. Thanks for the questions. So yes, I will come back to these big questions of what we know about celestial CFT so far, what we don't know. So I have a few minutes left before I go into the last section of this summary and outlook. Just the last thing that I would like to tell you is that there is a way to access the operator product expansions or OPEs in celestial CFT. No, it's not 3.2 at all. 4.2. The operator product expansions by looking at collinear divergences in the 4D momentum space. So the statement, and you will see why this is the case, collinear divergences of the 4D momentum usual stuff. So again, it's really bottom up. We'll start with all this beautiful formula people have been developing in scattering amplitudes and see what it infer. We can deduce in the celestial CFT. So these things extract for us the singularities celestial OPEs, and there is a very stupid reason for that. That you remember when we parameterize the momentum of the particle like so. Outgoing momentum. If you take the product of two momenta, P1 with P2, just compute that, and you find that is given by omega1, omega2 times Z12, Z bar 12, where Z12 is the difference between Z1 and Z2, and similarly. So in other words, a collinear limit, when the two momenta become parallel, selects, well, if you have a collinear divergence, it will extract the pole when Z1 approaches Z2. So basically, linear P1 or P2 is the same as taking Z1 close to P2. So in other words, you have a scattering you take these two momenta to be linear. These correspond in the celestial sphere to look at Z1 approaching Z2. Okay, then you have other. So you just take these 2 points to be close to each other. And then you have other insertions. So this very simple kinematic observation can also be used to now extract OPEs in celestial CFT. So I'm a bit running out of time here. So if you have questions about that, you can ask me in the discussion session. But let me just mention a few results on that. So if you look at graviton, want to derive graviton OPEs, you can do so. Let's take, for simplicity, 2 positive helicity graviton. So these are represented by 2 operators with j equal +2. They can depend, have each they carry a conformal dimension. So the computation has been done in this paper. I want to look at. So they are basically 2 ways to derive the OPE that I'm going to write down. The first method is brute force, namely you just do your Mellin transform and you do your collinear limits, and you can compute it. So method 1 is force, namely star for momentum amplitudes. Look at collinear divergences. There are formulas for that. Do the Mellin, do the collinear limit, and you will extract this structure. So this has been computed. If you have mixed helicity, it's a bit more tricky. But now people start to know how to deal with things. So this is the OPE you get, where beta is the Euler beta function. The product of gamma. So this is a computation you can do. And this second method, which is a bit more cute, is to just use symmetries. So that's one of the very great things of these infinite dimensional symmetries, that they are so powerful that they fully constrain the OPE coefficient. So you can actually don't do any computation, but just if you remember that you have translation invariance and the constraint implied by the leading soft graviton theorem, you can see that the symmetries, actually, little asterisk, you also have to know about the sub-leading soft graviton theorem I didn't talk about. But the main message I want to convey is that these symmetries, symmetry constraints, so you don't have to do this computation. They are powerful enough so as to they actually imply some sort of recursion relations on the OPE coefficients. Before you knew that it was a Euler beta function. So as to imply recursion the OPE coefficient. Actually, to uniquely determine the OPE coefficient. So the symmetry you need in this case, you need translation invariance, you need the leading subgraviton theorem. The subleading subgraviton theorem doesn't impose any constraint because by definition we are working in this SL2C basis. So this is already implemented. And you also need the subleading subgraviton theorem that I didn't talk about. So you can derive this, you can derive gluon OPEs, you can compute all sorts of things. And before I go to the summary, let me mention some comments about which is related to this OPE and these currents. And it's the more recent literature. But with that, we have almost covered the main features of celestial amplitudes. Is this observation that so that delta equal 1 and 0 up to whatever this shadow transform is conformally sublimit lead to celestial currents. But our recent work have been showing that there seems to be an infinite tower of currents where delta is running over all negative integers. So, and very recently, Strominger managed to show that if you look at this very complicated structure implied by these infinite towers of current, you can nicely, by a clever field redefinition, you can nicely recast this constraint in terms of a single simple algebra. Well, not so simple, but which is the so-called W1 plus infinity algebra, which is an algebra which appears in very different contexts in higher spin, but also in twister space. So now there have been this new interplay between celestial holography and twister techniques. So again, this is a nice combination of different communities working now together. So unfortunately, I don't have much time to talk about that in more details. And I will just, I think, go to the summary of what we have learned in these 4 lectures, and what are the main questions that remain to be answered in celestial holography. So summary and outlook. So what we have seen, and I hope I've tried to convince you that you remember that the infrastructure of gravity in asymptotically flat spacetime is very rich and very subtle. We have this infinite tower of symmetries of conservation laws that any consistent quantum theory, quantum gravity theory should obey. They have an infinite amount of symmetries which are constraining it. And celestial holography, the main point of this program is to make the full use, as much as we can use, of all these symmetries to constrain the holographic dual of 4D gravity. So which again, the main claim, or the main thing we are looking after, the theory of quantum gravity in flat space-time in 4 dimensions, which I recall describe the real world to some extent, could be described as a celestial 2D CFT living on the celestial sphere. And this there is this promising dictionary which involves this Mellin transformal integral, which makes this SL2C transformation manifest. So we have, to summarize and to finish, we have a similar feature that we are used to in usual CFT2. So the whole point is to understand what is the celestial CFT2? Does it make sense as a theory? How can we push this, and how can we constrain this quantity and this right-hand side here? So let me mention some nice feature that we have seen. So the main resemblance we've seen compared to usual CFT2 is that we have 2D currents, we have a Kac-Moody currents, we have a stress tensor, which is far from obvious. We have primary operators. We have also the descendants and so on and so forth. But they're also very different. This theory is also very weird to many regards. So let me mention some funny feature we have seen. So first, we had the fact that this conformal dimension of this primary is a priori any continuous and complex spectrum. We have seen that there is the super translation symmetry give an infinite amount of constraint that we are not used to in usual CFT, because they shift the weights of the operators by 1, as I've written in the formula before. Shift the conformal dimension by 1. And there are other things I just throwing at you, but I had some question before regarding that, so it's maybe a time to answer. So for instance, if you look at the 4-point function of in the celestial basis, you will see that it implies that the cross ratio has to be real, and all the points are actually forced to be inserted. This is just a constraint from kinematics. They are forced to lie on the equator of the celestial sphere. Just a constraint from kinematic. And this is something that we don't have in a usual local unitary 2D CFT. There are also weird things happening with the conformal block expansion that people are trying to treat the best as possible, but this is also something that is not so fully understood so far. And in the last minutes, let me tell you what are the big questions that are left to answer before I take all questions you might have. So of course, this is a very broad topic. I didn't have to cover all aspects of it. And this was biased on my own personal taste. But one question you could have is, what is the relationship? Or is there some way to use what we know from ADS CFT? How could we relate the celestial correlators to the one of ADS? But really, celestial holography is very different from ADS CFT. So in ADS CFT, we have this nice time-like boundary of ADS. But for flat space, gravity in flat space, we have this annoying null boundary, and this is what all the difficulty comes about. Because in ADS, what we are used to is we're used to put some reflecting Dirichlet kind of boundary condition, where we say that ADS acts like a box. But now in flat spacetime, as we have seen, we have gravitational wave escaping the boundary. So there is some leak of radiation that we have to account for. So I think we have to deal, if we want to make this relationship precise, we have to understand how to deal with leaks of radiation in holography. So that's the first point. The second point we already discussed, but this amounts to say, what is a celestial CFT? Namely, can we come up with the intrinsic definition rather than this bottom-up approach that most of the works have been following? Or intrinsic definition, or a list of properties, full list of properties that this theory should obey. Because so far, it was mostly bottom up from what we already knew from amplitudes. And we want a top down. We want to start with the CFT and infer something we didn't already know in quantum gravity. And I think that in this regard, we are starting to do so, because this nice symmetry structure that is emerging has compelled us to reconsider many aspects of gravity in flat space. We had to look deeper at new kinds of memory effects, new kind of observables. We had to relax very much this Bondi-Mesner-Rosex expansion that I showed in the beginning. And we start to understand how all these things are connected to each other. So I think that we are getting there slowly. And finally, I think one very ambitious goal, which is actually at the core of my own research project, is to have some sense, or to eventually use this program not to constrain just assembly flat spacetime, but spacetime which contain a horizon, which have black hole inside. In the presence of a black hole, this story is way more complicated. But eventually, I think that this paradigm can really learn. We can really learn something new in terms of conservation laws. What are the global conservation laws that black hole spacetime have to obey? So before I finish, I wanted to thank you for coming to the lecture and for your very interesting questions and comments. So thanks.
Hello, Kevin, can you hear me?
Yes, I can hear you.
Okay, good. So let's wait a couple of minutes. People is still coming in, and then.
Okay.
Okay, great. Okay, so welcome for the last lecture by Kevin on remote. So please, Kevin, you can start.
Okay, thank you very much. Actually, so for this lecture, I actually didn't get a chance to prepare slides in advance, so I'm going to write as I go. And what I want to discuss today is how to do some computations with Witten diagrams, just like in traditional ADS-CFT, but in this topological string context. So what we're going to do is we'll build a chiral algebra by studying the topological string on SL2C. I'm going to do what we've done so far. We've related infinite dimensional symmetry algebras on the gauge theory side and the holographic dual. We've seen that these are the same. And the main result we'll be able to do today theorem, which will use this fact in the proof. The planar gauge theory chiral algebra is isomorphic to the holographic. So we'll be able to show that we can match all of the OPE coefficients, and in particular, all correlators. So the first thing we need to do to understand this is to understand how to build the holographic chiral algebra. So we started discussing this a little bit yesterday. So recall from yesterday that SL2C has a compactification where the boundary is CP1 times CP1. So I'm going to give an explicit description of the geometry near the boundary. Just on a patch near the boundary, we have coordinates Z in C. This will be the chiral algebra plane. So this can be thought of as the boundary of ADS3. W in CP1, and also N, which is normal to the boundary. Now, N really lives on a line bundle over CP1. As I explain in a second, it's related to the Hopf vibration, which means that N has a pole when W is infinity. In other words, N transforms like dW to the half, like a spin half field. So these coordinates we're going to use are related to the coordinates on ADS3 times S3 as follows. If we write N equals or e to the I theta, then Z, Z bar, and or are coordinates on ADS3, really mutating ADS3, and the boundary is or equals 0. W bar, and theta are coordinates on the 3 sphere, which we're seeing as a Hopf vibration over CP1. The theta coordinate parameterizes the Hopf fiber. So that's it. So the goal is to build a chiral algebra living on the Z plane by studying Hopf and the gravitational and gauge theory we have in the book. So to get there, we need a few more details of the geometry. Well, Z is not a holomorphic coordinate. There is a Beltrami differential. Which looks like mu is factor of n. I'm going to drop some factors of pi, n squared So this may look a little funny, but if you remember that n transforms like the square root of dw, so n squared transforms as w, this expression here includes the natural volume form in CP1. So it's a natural expression. And also, because our bulk theory, we're going to be focusing on the open string sector because it's easier. And the bulk Lagrangian is the holomorphic Chern-Simons Lagrangian. So that involves the holomorphic volume form of this geometry. So I need to write that down too. Omega, it has a whole of order 3. Let me just look at my notes. Calculated in these coordinates, looks like this. So it's important to note that if we look over here, there will be a piece of this which looks like d theta d times the volume form in the two-sphere times n. So from this, you see that the integral over the 3-sphere of omega is equal to n, as we would expect. Okay, so far we've just set up the coordinates. Are there any questions?
No question at this stage.
Okay, I actually can't see you guys anymore for some reason, but it's no big deal. So recall the holomorphic Chern-Simons Lagrangian. We're going to have a gauge field, because there's 0, 1 form in this geometry, valued in SOA. And it looks like half integral trace a d bar a plus 1/6 trace a. And this whole thing is hit with the holomorphic volume. So to describe the holographic chiral algebra, we have to first describe boundary conditions at n equals 0. This is on the boundary of our geometry. And then states will violate the boundary condition at some value of z. The natural boundary condition, if you spend a little time thinking about it, it's a little subtle, but we notice that omega has a pole, order 3. It turns out that asking that a has a 0 is a good boundary condition. So if we ask that a goes like n, near n equals 0, is a good boundary condition. Wait, so now we can ask, what is a state? And the answer is, of course, we're going to modify the boundary behavior at some value of z. For example, we could ask, that a goes like a delta function at z equals z0 plus on. This is going to be the simplest, lowest lying state. So in a moment, I will match these with the states in the chiral algebra. But for now, well, if one studies ordinary ADCFT, he might say, well, what you really want is a solution to the equations of motion on the bulk geometry, which satisfies this boundary condition. And we can find such a thing. You can show that there is a unique up to gauge equivalence solution to the linearized equation of motion, which is just the d-bar equation, which satisfies this modified boundary condition. So this, the explicit formula is A, say C0 is, let's introduce a color index, dA plus right factors and drop some factors of pi, it's going to look like this. So the reason this satisfies the equations of motion, we should recall that there was a Beltrami differential, so z wasn't holomorphic. So if I take a delta function at a fixed value of z, that doesn't satisfy the d-bar equation. But this, adding on this correction term makes it so it does. So I can draw a little picture about what this is. Here we have ADS3. This is the boundary of ADS3. My state.
Sorry, Kevin, the H in the second term is TA, is multiplied by TA or what?
Yes, the second term is multiplied by TA as well. So. Thank you. Right, so what this looks like, as I approach the boundary is at n equals 0. As I approach the boundary, it decays rapidly here. So it's 0, 0 as I approach the boundary. But if I move a little bit away from the boundary, it also decays. So this should be z minus z0. My apologies. It decays as z moves away from and Z0. So this is the kind of thing you want for a state, right? On the boundary, it's localized at a particular point. As you move away from the boundary, it spreads out away from that point with some particular decay rate. The decay rate, of course, will be related to the 2-point function. And that's good because this state is related to the current, and the 2-point function of the current goes like 1 over Z squared. Okay, so we're going to propose that AA Z0 gets matched to the state JA Z0 in the chirological, where this is the SOA current, and that's written as and then there's some. Let me write my color indices like that. Or an S1 from 1 to 8, and it's anti-symmetric of ORS. So we'd like to also build the states that correspond to or to these symmetrized traces. So which we and what we'll find is that the ways of modifying the boundary condition at this point match precisely with the states in the CFT. So let's think about the most general way we can modify the boundary condition. So we could say A is like delta function at Z equals Z0, but there's nothing stopping me having more singular behavior in N. So I could have 1 over N to some power, okay. And once I have that singular behavior in N, you could also think, well, why can't I have a function of W2? And the remaining terms are going to be terms which are less singular in N, whose inclusion will be forced by solving the equations of motion. Now, what possible values do we have here for these indices? Well, I can have an arbitrary pole in N, but we know that N has a pole at W equals infinity. Which means 1 over N to the K has a 0 of order K. Having a pole in the W plane would be bad because it would prevent my field configuration from satisfying the equations of motion. So we need that the index L ranges from 0 to K. Well, this is perfect because these are exactly states with the right quantum numbers to match the states we see in the chiral algebra. So we propose that this corresponds to the color factor. This corresponds to I or x1 L x2 k minus L I s. And these states have the same quantum numbers. Okay, any questions so far?
Nope.
Okay, so I assume everything is crystal clear. So now we've described the states on the holographically dual side, we can ask, how can we compute their endpoint functions? Let's say the 2 and 3 point functions to start. Well, so the endpoint functions of these states are computed in principle by Witten diagrams. So let's start with the 2 point function. So if I take my state A Z0, okay, let's go, n squared dw bar. Oops. I take 2 such states. Their 2 point function is obtained by inserting into the kinetic term of the homomorphic Chern-Simons font. It's going to be integral over all my coordinates of A 0 d bar AB be 0, and then when we contract indices, there's going to be a delta AB. Sorry, Z1. So since these states correspond to the SO8 current in my chiral algebra, these have a 2-point function which goes like n delta AB over C0 minus C1 squared. So this is what we would like to reproduce. So just to remind you, the factor of 1 over Z0 minus Z1 squared, you can see this because that's the standard central extension of the Castiglione. And it contains a Castiglione at level n just because that's the number of fields we have. We can also see it from these guys are like I, X is in the middle. And when I contract them, we do 2-way contractions. And there's a loop in the middle. So the loop in the middle contributes n, and the 2-way contractions contribute 1 over Z0 minus Z1 squared. When I forgot the crucial point to introduce the volume formula. So let me scroll up a little bit so we can see the formulas for these expressions. Each expression is pretty much the same. Here there'll be like a delta C and C1, and here there'll be the same kind of thing with the 1 over C minus C1 squared. So what I'd like to do is kind of quickly compute this integral explicitly. And we're going to be a little loose, and I'll drop some terms which are not so important and just focus on the relevant terms. I can take the first one. I'll drop the color factors too. This one to be a delta function. Here, I'm going to put d bar of let's see. Let me do this. R A 1, and the volume form looks like dn or n cubed dw dz. This is the relevant term of the volume form. And because our geometry is non-compact, we're going to integrate over z and w, or n is, we're going to introduce a cutoff near the boundary of ADS3. Now, if we do integration by parts, this is a pure boundary integral. The boundary term, we're going to get rid of the d bar. And we're going to find something like this. And n squared dw bar 1 plus w squared squared dn or n cubed dw dz. Oh, and I forgot a crucial term, which is 1 over z minus c1 squared. This term here really appeared originally over here. Okay, so all I've done is, you notice the integral is a total derivative, so you pick up the boundary term, and we just insert all the terms, and we get something that looks like this. And now we see we get a really nice answer, because this will correctly reproduce the chiral algebra 2-point function. Why is that? The integral over w of dw bar 1 plus w squared squared. This is just the natural volume form in CP1 for the Fabini study metric. So this is basically 1. It's a multiple of pi. So that part goes away. The integral over z well, because I have a delta function in the integrand, all that does is produces 1 over z0 minus c1 squared. And that looks good. And finally, we have an integral contour integral over n. And we notice up here, we have an n squared, there we have an n cubed. So we get contour integral over n of dn over n, and that gives you, 2 pi I, which is also important. So we do indeed find that the holographic 2-point function is correct. Okay, any questions about this calculation?
Yes, there is a question.
Hi, Kevin. I just got a little bit confused. Is the integral, if you go up just before you did the integral,
Right there?
Is this an integral over CP1 times CP1, or is it over S2 times S3?
Right. Well, up here, this was an integral over SLTC, but I've removed the neighborhood of the boundary. So here, when I go down to the boundary integral, this is really an integral over an S1 bundle over CP1 times CP1.
Yeah. So where's the fifth coordinate then? I'm just got confused.
It's n, you see, because n, the absolute value of n is fixed. So we're left with the angular value of n, and that's the fifth coordinate. And that appears when we it's an integral, so I can just compute it in a dense open set as long as it converges. So I don't worry too much about the fact that it's a non-trivial circle bundle. So in which case the integral becomes an integral over c times S1, and the integral over the S1 just gives us this contour integral here. Does that make sense?
Yeah, thanks.
Okay. So how about the 3-point function? Then we will play the same game. If I take 3 states, we're going to get like with f, a, b, c integral with a 6-dimensional geometry. Phrasing it like this, though, it turns out to be a little tricky. And I personally prefer, well, in any holographic computation, I prefer to use the OPE rather than the 3-point function. So how do we define the OPE? Well, the OPE, the object which when inserted into the 2-point function gives with AC gives the 3-point function. So what is that? This is just the definition of the OPE in general. But there's a nice formula for it. The OPE is given by d bar inverse of this expression is the OPE. And you can imagine it as follows. There's my first state. And then here, d bar inverse is the propagator coming off like that. So why is this the OPE? If I insert AC, C2 times d bar of that. Well, clearly the d bars cancel. Is the 3-point function. So the OPE is something that's actually easier to compute than the 2-point function. So let me quickly explain the technique for doing that. So the technique for computing the OPE is, well, A, C0, looks like this. And it turns out that this is d bar TB times d bar of 1 over c minus c1. So I can remove this state by a gauge transformation. However, in the presence of the other state, this gauge transformation has a non-trivial effect. It sends this other state, C0 to 1 over C0 minus C1, FABC, TC, delta Z equals Z0, plus the other term. Now here we see the correct Casmudi OPE. And of course, one can play this game with all of the other states, so it's a little more complicated.
There is a question, Kevin.
In the last equation, how does the B index get soaked up? Because it remains free on the right-hand side, but on the left-hand side, it's just AA.
Right, so the B index is present in the gauge transformation. The gauge transformation is like
Oh, I see.
B over C minus C1. And I'm looking at the effect of this gauge transformation on this field.
Thanks.
Okay, so in this way, one can, in principle, or just by working really hard and thinking about standard Witten diagrams, try to compute all of the correlation functions of the higher algebra. However, that's really hard. And there's a shortcut. The shortcut is that we know, we've already checked that on both sides there's this really big symmetry algebra. And that's going to constrain everything really tightly. And that will really help us to cut down the problem to a much, much simpler problem. So let me very briefly say how, it's already kind of obvious that this symmetry is present on the holographic side because it's just the gauge transformations. But it can be helpful to think about the mode algebra from the holographic point of view. So just like a local operator is obtained by modifying the boundary conditions at a point, so we get a field that looks like a delta function at a point on the boundary, a mode will be a field configuration like, for example, some power of z, a delta function that's where z is on the circle. Maybe there might be some negative powers of n. Plus some other stuff where the negative powers of n are localized on the circle. So we need to see, commutators of modes can be computed using the same gauge transformation trick we just mentioned. So I want to briefly explain why does functions on SL2C, these are holomorphic functions, tensor SO8, live inside the mode algebra. The answer is very simple. If I take f, which is a holomorphic function on SL2C, f times TA times the delta function at z equals 1, this expression satisfies the field equation. Call this A. Even though Z is not holomorphic. So geometrically, what we're doing is we're just taking our holomorphic function and multiplying it by a delta function on a 5 manifold, which at infinity goes to this circle where Z is 1 like that. And the reason this satisfies the field equation is just this is closed. The delta function, any 5 cycle is a closed one form, and d bar f is 0, because it's a holomorphic function. So in this way, we see that this global symmetry algebra really lives inside the modes of our chiral algebra. And how does that help us? We know that the commutators of modes of our states are given by the algebra functions in SL2C, SO8. Now, if I take in any chiral algebra, the commutator of modes is some expression in terms of the OPE coefficients. So this relationship, it turns out to constrain all OPEs. And so correlation functions uniquely except the 2-point function of the stress energy tensor, which goes like n squared. So in other words, once we know this result, that we have this huge symmetry algebra, and once we can identify the quantum numbers of the states, everything else is determined by a single parameter, n. We conclude that the holographic algebra is isomorphic with planar CFT offer. Okay, so I think I'll stop there.
Thank you. Thank you very much. So let's start the discussion session. Yes, okay.
Hi. At the beginning, you mentioned something about a Hopf vibration. Is this a